GATE 2020 Thermodynamics. When 1 mole of C3H8 at 300 Kelvin is burnt with stoichiometric amount of oxygen at 300 Kelvin to form CO2 and H2O, the adiabatic flame temperature is 5975 Kelvin. If this propane is burnt under the same conditions with excess oxygen, the adiabatic temperature will be. See, whenever you see for an adiabatic flame, it means that whatever heat which is being generated, all will be consumed to increase the temperature of the flame itself. But here is asking, if you'll increase the oxygen, it's right that it increases the adiabatic flame temperature. But after certain excess amount of oxygen is given, will that affect the adiabatic flame temperature or not? We'll get to find it out. Suppose C3H8 is burned to form CO2 plus H2O. This is not balanced, so we'll try to balance it with, okay. And now you should also remember 1O2. So it is nearly 8O2 and 3 carbon, 6 plus 4, it is 10, 5O2. So here you should remember that the C3H8 has the same condition with the adiabatic flame is burnt with stoichiometric amount of oxygen. Okay. Now, you see for an adiabatic, the delta H will be 0. This is at 298 Kelvin and this is at 5975 Kelvin. Okay. Now, there won't be this path here directly. So, when you heat it from 298, directly all the heat will be consumed here to form the CO2 plus 4H2O mixture at 5975. 3 CO2 plus 4H2O at 300 Kelvin. Now, here, suppose if you increase the oxygen here, now if you will calculate the delta H, it is nothing but the Cp of the H products minus reactants into its temperature difference. So it is 300 to 5975 and Cp of 3 times Cp of CO2 at this one, my plus 4H2O, okay, dt. So now, whatever oxygen you are providing, suppose if I'll increase 1 mole of oxygen here, so that mole of excess oxygen is not utilized in the consumption of reaction itself, because whatever heat is coming will be utilized to increase the temperature. Now, whatever excess oxygen you are providing, it will stay there as an excess in the product side itself. So here, if you'll see, for the calculation of dt or adiabatic flame temperature, it is delta H by Cp of 3 Cp of CO2 plus 4 Cp of H2O plus if there is an increase in excess amount of moles towards the product side, here also the moles of oxygen will start. So overall, the adiabatic flame temperature, when there are excess oxygen, the adiabatic flame temperature decreases, because if you see theoretically also, the number of moles which are there in the product side, it also consumes the reaction. So whatever, depending on the amount of higher or lower, the temperature of adiabatic flame temperature will be decreased. So lower than the 5975, irrespective of the amount of excess oxygen, even it is 1 mole or 2 mole, that increase will not increase the adiabatic flame temperature, will try to decrease it. And let's see corrosion 2020 questions. Which one of the following is an example of electrolytic cell? The corrosion in the metal rod in ambient temperature, charging in a rechargeable battery, and the discharging of a recyclable battery, sacrificial cathodic protection in the system. See, let's see what are the difference between electrolytic cells and galvanic cells. If you'll see, the electrolytic cells are the type of cells which converts, the galvanic cells are type of cells which converts chemical energy to electrical energy. And the reaction is very spontaneous. And here there will be anode and a cathode. And in electrolytic or the electrolytic cells, the purpose is they convert the electrical energy into chemical energy. And the reaction is little non-spontaneous, not very fast as the galvanic cells, and there will be an anode and a cathode. What happens at an anode, at anode, there will be oxidation. Okay. And at cathode, there will be reduction. The Cu plus 2 will convert to Cu. This is called reduction. And oxidation is Zn giving Zn plus 2, and losing of electrons is oxidation. Gaining of electrons is reduction. So you'll see the anode polarity also in a galvanic cell, anode polarity is negative, and for a electrolytic cell, anode polarity, the polarity if you check, anode polarity is positive. For cathode, it is negative polarity, and for here it is. And electron flow from anode to cathode simultaneously. The example for this is electrolysis, splitting of water. Example for this is batteries, Daniel cell. These are the fundamental differences. So if you'll see the electrolytic cell, it will be discharging of the discharging of a recyclable battery. And discharging of a recyclable battery is a galvanic cell. So here it is charging of an, so you're converting the electrical energy into chemical energy. That is charging of a recyclable battery. The iron plate with total exposed surface area of 50 centimeter per second undergoes an atmospheric corrosion of 200 grams, and the weight lost is over a period of time. Then the corrosion rate is, so for calculating corrosion rate, we know corrosion rate is nothing but the weight which is given by area into time. Weight is given as 200 grams. Okay. And area is given as 50 centimeters square. So we'll convert this into meters. And then time is given as 10 years. So as a reaction is, the rate is being asked at kg per meter square per year itself. I'm leaving this in years. This comes to 4 kg per meter square per year. The answer is 4. The galvanic cell is formed by connecting zinc and iron and the wires immersed in respect of their ionic solution, and the reduction potentials are given. The cell discharges spontaneously with a voltage of 0.4. The voltage of 0.5, the ratio of concentration of Fe plus 2 to Zn plus 2 ions in a cell is of order of. So, like zinc gives Zn plus 2. If you see in an EMF series, zinc will be above iron. So zinc will be anode here, and this will act as cathode. So zinc will become Zn plus 2, and iron plus 2 will become iron. So the overall reaction will be, redox reaction will be Fe plus Zn plus 2. Now, according to the Earnst equation, E of a cell equal to E naught cell minus 0.059 by m log of product concentration by reactant concentration. E naught of cell is E cathode minus E anode. E cathode is given as minus 0.44 minus of minus 0.76 E anode minus 0.059 by 2 into log of Zn plus 2 by Fe plus 2. So E of a cell is given as 0.5. So calculating this, Zn plus 2 by Fe plus 2 is 10 power 6 minus. The answer is 10 power 6. It is asked as Fe2 Zn plus 2. The iron is corroding in a fresh water which has dissolved oxygen concentration of 15 millimolarity. The anodic current density at an over voltage of 120 millivoltage is over potential is given as. So if you'll see 120 millivolts of over potential is given. Anodic Tafel slope is given as 0.06. Diffusion coefficient of oxygen is given as 2.42 into 10 power 4. And diffusion layer thickness is given as 0.06 centimeter. So if you'll see, exchange current density is given by I naught, which is equal to Z into F into dc by x. You can get this from diffusion law, d into dc by dx. Okay, and this can be written as uh, I naught by ZF. Okay, this I by A is the I naught, which is exchange current density. So you can get this as 0.5 into 96,500 into diffusion is given as 2.45 into 10 power minus 5 into concentration is given as 15 millimolars. So it is by 0.06, which is equal to 0.291. Now you need to calculate the anodic current density. So how you get anodic current density is from Tafel equation. In a Tafel equation, over voltage, the over potential is given as 120 millivolts. So over potential is given as beta log Ia by I naught, where I naught is the current density and I extend current density, and Ia is the anodic current density which we need to calculate. So this is given as 120 into 10 power minus 3 is equal to 0.06 log Ia by 0.291. It implies Ia is equal to, so let's calculate this, 0.201 ampere per centimeter square. Okay, the metal oxidizes at 1200 Kelvin. With a parabolic rate constant of 3 into 10 power minus 6 gram per centimeter power 4 per second. The time taken for the oxide film to grow to a thickness of 2 micrometer is dash seconds. The density of oxide is given as 6.5 gram per centimeter cube. So use parabolic rate law. Is W by A is equal to root over KT. Or parabolic law is nothing but W by A is KT. Logarithmic law is log of W by A is proportional to KT. Linear law is W by A is KT. Okay. So this is equal to the weight can be written as density into volume per area. So you'll get density by x is equal to root over KT. So T is equal to K is equal to 0.56. The oxide thickness is given as 2 into 10 power minus 6. So density, parabolic constant is given as 3 into 10 power minus 6 gram per centimeter cube, and density is given as 6.4. Substituting these values together. Yeah, thank you.